Hi guys, more financial maths here. Looking at text and test 5, page 155 here. And we are looking at questions 11 to start with, and then 5 and 10 we'll come back to. So I want to start with this idea of what is the present value of a sum of money. Well, that is, how much is a promise of money today worth? How much is a promise of money in the future worth today? Okay, so let's suppose you have a bank account that pays a 2% interest rate. If I promised you €100 in 3 years' time, the value of that €100 today would be €94.23. Okay, so it's the present value formula, 100 divided by 1.02 cubed. The reason for that is you could take that €94.23, and now that's been rounded, so this might not work out perfectly to 100, but if you put that in your bank account earning 2% interest for 3 years, you come out with €100. Okay, so what's that? 94.23 times 1.02 to the power of 3. Okay, so you can see there 99.997, that's €100. Okay, so that's the present value of €100 in 3 years' time, assuming an interest rate of 2%. Or that's often called a discount rate, okay? But they mean the same thing, discount rate, interest rate. But that's the future value, the present value of that €100, okay? Well, question 11 says, show how the present value of an annuity involving depositing €3,000 per year in an account for 6 years can be written as a geometric series, given that the interest rate is 8% per annum, okay? Assuming each payment is made at the start of each year. So let's suppose somebody very generous in your life decides they want to give you €3,000 every year at the start of every year for the next 6 years. And you say, well, that's very good, but could I just have it all right now instead? They might say, yes, but this €3,000 that I'm paying initially, that's going to be paid today, so that's €3,000. This €3,000 I'm going to pay in a year's time is not actually worth €3,000 today. It's worth less, okay? Its present value is 3,000 divided by 1 plus my interest rate, which in question 8 is 8%, so 1.08. That's the present value of that €3,000. The next €3,000, well, that's going to be paid in 2 years' time, so it has a present value of 1.08 to the power of 2. And the 3,000 that's going to be paid in 3 years' time has a present value of 1.08 to the power of 3. The fifth payment has a present value of 3,000 times 1.08 to the power of 4. And the sixth payment has a present value of 1.08 to the power of 5. So if you ask for all of that money together at the same time, they might say, well, yeah, I can give you that money, but it won't be 3,000 multiplied by 6. That's not what you get. You get this much money. And you'll say, well, how much is that? Okay, so can we work that out? Well, yes, of course we can. That's a geometric series. If you look here, you're multiplying by 1 divided by 1.08 at each stage in this geometric series. Okay, so you've got a common ratio of 1 over 1.08. Okay, so if you want to work out how much that's worth, you'll say, well, my first term is €3,000. My common ratio is 1 over 1.08. And how many terms do I have? Don't make the mistake of looking at the indices. 1, 2, 3, 4, 5, 6 terms is what you have, okay? So the sum of all of that money is going to be, what's our formula? Sn is A times 1 minus r to the n over 1 minus r. So 3,000 times 1 minus 1 over 1.08 to the power of 6 over 1 minus 1 over 1.08. Okay, now those calculations can be a bit tricky, so I would suggest you pause the video and work that out yourself. I have it worked out here. Okay, welcome back. The answer is 23,000 €768 and 41 cent. Okay, so that is what each of those payments, the sum of those 6 payments, if you paid it today, is. So you might have thought it was going to be 3,000 multiplied by 6 payments. You might have thought, excuse me, what have I done funny there? Have I taken down the wrong number? I have. Excuse me. That number is €14,978. Sorry about that. And 13 cent. Okay, now you might have thought it was going to be 18,000 for 6 payments of 3,000, but that is not the case. No. The next question says, well, what is the future value? Calculate the future value of that annuity. Okay, the future value of the annuity. Well, what does that mean? That means if this is being paid into a bank account for you every year, and the bank account was earning 8%, well, that first 3,000, and you're not touching anything, so that first 3,000 sits there for 6 years. So it's going to have a future value of 3,000 times 1.08 to the power of 6. Excuse me. The next 3,000 euros sits there for 5 years. Excuse me. And so on. The last 3,000 euros sits there for 1 year. Okay, so how much is this all going to be worth if you leave it in a savings account earning 8% every time that 3,000 euros comes in each year? How much are you going to have in the end? Okay, well, that's again a geometric series. Your first term is back here. Remember, we work backwards on these ones. 3,000 times 1.08. Our common ratio, well, you're multiplying by 1.08 with each step, aren't you? So our common ratio is 1.08, and our number of terms again is 6. So the sum of that geometric series is 3,000 times 1.08 to the power, just 1.08, multiplied by 1 minus 1.08 to the power of 6, all over 1 minus 1.08. Okay, and this is the one that is 23,768.41. Again, I'd encourage you to do that calculator work, just to make sure you're happy with it. The last part of the question asks you to relate this number and this number. Okay, because if you took that present value of that money, okay, and you put it into your bank account now, you'd say 14,978 euros and 13 cent. And if you put that into the bank account that earns 8% interest and you left it there for 6 years, how much would you get? Well, it turns out you get the exact same as if you've been saving that 3,000 euros every year over the 6 years. You get this 23,768 euros and 41 cent. Okay, I'll just show you that. 14978.13 times 1.08 to the power of 6 equals, okay, 23,768 euros and 41 cent. So there's question 11. If we turn the page here, question 5 is a little bit more abstract, so I'm working backwards here. But question 5 says, show that the present value of a series of n payments of p euros earning an interest rate of I% per annum can be written like this. Okay, so question 5, p payments. So our first payment is going to have a present value. Now these payments, this is working up towards our mortgage formula. So payments are made at the end of a payment period. It's at the end of the month. It's when you pay your mortgage usually. So the present value of all of those payments, well, the first payment you make of size P is going to have a present value of P over 1 plus the interest rate. The next payment you make, so that's at the end of the first month. At the end of the second month, P over 1 plus I squared plus, you do that the whole way. At the end of the nth month, P over 1 plus I to the end. Now I'm saying month, but this could be year, this could be any time period you might be repaying a loan or repaying a mortgage over. So what do we got there? We've got a geometric series. First term is p over 1 plus I. Common ratio is 1 over 1 plus I. If you look, that's our term to term rule, is multiplied by 1 over 1 plus the interest rate. And how many terms do we have? We have n terms. So the sum of all of those n terms is going to be a times 1 minus r to the power of n, all divided by 1 minus 1 over 1 plus I. Okay, so that's the same formula we've seen the whole time. It's a little bit untidy just because you've got those fractions inside fractions. So to tidy it up, I'm going to multiply here. Let me rewrite it. That's p over 1 plus I times 1 minus, well, 1 to the n is just 1 over 1 plus I to the power of n, divided by 1 minus 1 over 1 plus I. Okay, so to tidy that up, I'm going to multiply top and bottom of this fraction by this 1 plus I to the n. And that's going to get rid of this fraction, which is nice. And here it's going to actually get rid of this fraction as well, because that has a factor of 1 plus I. Top and bottom. Well, what do I get out of that? The first part doesn't change, p over 1 plus I. Inside the square brackets now, multiply top and bottom. Well, if you multiply the top by 1 plus I to the n, 1 becomes 1 plus I to the n. That becomes minus, well, 1 plus I to the n over 1 plus I to the n is 1. All over, this is 1 plus I to the n minus 1 over 1 plus I. So minus 1 plus I to the n over 1 plus I, which is 1 plus I to the n divided by 1 plus I is, well, that's minus 1, okay, because that's the same thing in the bottom. So let me just show you what you might be looking at there for that last bit. If that said x to the 8, if n was 8, divided by x, well, that would be the same as x to the 8 minus 1. So that's where that's after coming from. Okay, so we nearly have what they want for us there. What do we have? 1 plus I to the n minus 1, yes, p, this thing has changed. So 1 plus I to the n on the bottom can be taken out as a factor. Okay, so let's do that. No, let's multiply this through. Okay, so that first bit, p stays where it is, top of this line stays the way it is, 1 plus I to the n minus 1. On the bottom, 1 plus I multiplied by 1 plus I to the n becomes 1 plus I to the n plus 1 minus 1 plus I times 1 plus I to the n minus 1 is 1 plus I to the n. And now we've got a common factor of 1 plus I to the n on the bottom there. So let's take that out. P over 1 plus I to the power of n times, okay, and the top doesn't change, 1 plus I to the n minus 1. On the bottom, we're left with, well, we've taken that out as a factor, so we're left with 1 minus, here, bracket 1 plus I, because we only took out 1 plus I to the n. So we're left with 1 plus I minus 1. Sorry now, that's gotten a bit messy. But on the bottom there, 1 plus I take away 1 is just going to be I, which is what they've asked for. This formula is very important when we work with mortgages, and we're going to see that in the next exercise. I'm going to